Welcome to EDU World Space.
In this question, we have three spheres, a 5 kilogram and a 10 kilogram sphere that are stationary, and a 0.1 kilogram sphere that is somewhere in between. And the 0.1 kilogram sphere is released from rest. And we are to calculate the speed of the 0.1 kilogram sphere when it has moved 0.4 meters to the right from its initial position. So let's start off with a diagram. I'm going to draw on the 5 kilogram sphere as well as the 10 kilogram sphere. And the 0.1 kilogram sphere starts in the middle here. There's a distance of 0.4 meters and then a distance of 0.6 meters. So the easiest way to calculate this, because of course you could use forces, but the easiest way to calculate this is to use conservation of energy, because we know that throughout the motion, as the 0.1 kilogram sphere moves towards the right, we know that there's going to be a change in gravitational potential energy. Whatever that change is will go into increasing the kinetic energy, and from that we can go ahead and calculate the velocity. So in that sphere, I'm going to start off by calculating the change in the gravitational potential energy. So we're going to use UF minus UI. And we need to include terms from both the 5 kilogram sphere and the 10 kilogram sphere. So I'm going to call the 5 kilogram mass A and the 10 kilogram mass B. So the gravitational potential between MA and 0.1 kilograms is going to be minus GMA times little m divided by the radius or the distance between them. So I'm going to label that as RA final. And then we're going to subtract a term for the gravitational potential between B and the small mass. And then, so that's going to be UF. And then we're going to subtract from that the same thing, but for the initial state. So subtracting a negative, everything in the initial part will become positive. And so we get something that looks like this. And then what I'm going to do is I'm going to factor out the G and the little m, just so we don't have to write that a bunch of times. And we'll get something like this. And then we'll just go ahead and plug everything in after that. So of course we have G, that's going to be 6.67 times 10 to the minus 11. And our little m is 0.01, or sorry, 0.1. Mass of A is 5. And that's going to be over the separation, the final separation between A and the small mass. So the small mass moves to the right, 0.4 meters. So the final separation will be 0.8 between those two. The separation between 10 and the small mass will decrease down to 0.2. And then we have our initial terms. The original separation is 0.4 for A, and then 0.6 for B. So rather than plug this in all at once, let's do a couple intermediary steps. So if we do 6.67 times 10 to the minus 11 times 0.1, that'll change that to 10 to the minus 12. And then the first two terms inside here are going to be negative 56.25, and the second two are 29.17. So once we plug that into our calculator, we get a value of negative 1.81 times 10 to the minus 10 joules. So that is delta U. But because of conservation of energy, we know that any change in the potential energy is just going to translate into kinetic energy. So the change in potential energy can be thought of the same as negative the change in kinetic energy. And that just comes from the fact that delta U plus delta K has to equal 0 for conservation of energy. So what that means is that delta K is equal to 1.81 times 10 to the minus 10 joules. And we can use this to get a hold of what's the final speed. So delta K is going to be 1/2 mvf squared minus 1/2 mvi squared. But we know that this mass starts from rest. So this term here is going to be 0 because of the fact that the initial velocity is 0. And so we can go ahead and isolate by for Vf by multiplying by 2 and dividing by the mass, which is 0.1. And then if we want to do it all in one step, we'll just take the square root of both sides. So once we've got that done, the final answer is 6.01 times 10 to the minus 5 meters per second. And so that will be the final speed of this mass.